Okay, so our chapter 1 quiz. First question, it's more of an application question, says the displacement in meters of a ball rolling in a straight line on a grassy hill is given by, okay, so here we have a function of s for displacement and t, where t is time in seconds. First it says find the average velocity over this interval. To find the average velocity, we're just looking for that slope. So we can write the average velocity as just sort of y2 minus y1, which in this case would be the function s at 1.5 minus the function s at 1 all over, again, x2 minus x1, which would just be 1.5 minus 1. So that's all you need to do for this one. You can figure out what s as 1.5 is. Just substitute 1.5 in for t, and you get minus 1.5 squared plus 3 times 1.5 plus 10. And you'd get 12.25. You can do the same thing for s at 1, which would be minus 1 squared plus 3 times 1 plus 10, and which gives you 13 minus 1, which is 12. Okay, so then we just substitute that. So we have 12.25 meters minus 12 meters all over 1.5 seconds minus 1 second, which gives us a speed of 0.5 meters per second. Part B wants the instantaneous velocity at t equals 1. So that's when we need to use the difference quotient, which is the limit. Yes, limits, right? As h approaches 0 of the function at 1 plus a little bit of h. Right? It's the same thing. It's y2 minus y1. It's just y2 is 1 plus a very tiny little bit minus that function at 1 all over h. We can't substitute h equals 0 now, because then we're going to be dividing by 0. So why don't we just go to the side here and figure out what s at 1 plus h actually is. So if we substitute this into our function up here, we get minus 1 plus h squared plus 3 times 1 plus h plus 10. Okay, so now we just need to expand. So that's a perfect squared. So you're going to have 1 plus 2h plus h squared. We can distribute the 3, so plus 3 plus 3h plus 10. And then you just distribute the negative and collect like terms, and you'll have minus h squared plus h plus 12. So now we can substitute this. So we get the limit as h approaches 0. We're going to substitute this one, so minus h squared plus h plus 12. And then we're going to subtract s at 1, which we figured out up here is 12. So 12 all over h. 12 minus 12 is just 0. And in our numerator, we can factor out an h. So this is the limit as h approaches 0 of h times by minus h plus 1 all over h. So now those h's cancel, and you're left with just minus h plus 1. But as h approaches 0, that goes to 0, and we're left with just 1 units meters per second. So the first one, for 2a, we're just going to evaluate the limit. You might be able to see the denominator is a difference of squares. So we can work with that. We can write this is going to equal the limit as x approaches 6. So we have x plus 6 on the numerator, and then the denominator, we're going to get x plus 6 times x minus 6. And so these will cancel. And that'll just give you 1 over x minus 6. Can't do anything more with that, and unfortunately when you plug in 6, it doesn't work. Right? So in this case, the limit does not exist. That's unfortunate. Let's try the next one. Maybe we'll have better luck. Alright, for the next one, we got that square root up there. So let's rationalize the numerator. We're going to multiply it by its conjugate. So square root of 13 minus x and then plus 4 over the square root of, has to be the exact same thing, plus 4. So by doing that, we pretty much create a nice difference of squares there on the numerator. We get the limit as x approaches negative 3. So we'll have 13 minus x, and then we'll have minus 16, because it's 4 squared, all over, and then we have this sort of mess on the bottom here. X plus 3 times the square root of 13 minus x plus 4. When you do that, notice we have a negative x on the numerator, and if you do 13 minus 16, you get minus 3. So what I'm going to do is I'm going to pull out a negative 1. And if I pull out a negative 1, I get x plus 3. I'm not going to change anything on the denominator. You can probably see where I'm going with this. I want to get rid of x plus 3. So when x plus 3 cancels, I'm left with negative 1 over this. As x approaches negative 3, we will get, actually I don't need to, I'm going to substitute negative 3 in there, so I don't need to write limit again. So I'll get negative 1 all over the square root of 13 minus negative 3 plus 4. So that's 13 plus 3, which is 16. Square root of 16 is 4. 4 plus 4 is 8. So we're left with minus 1 over 8. So what we're going to do with letter C, right, is I'm going to multiply it by x over x. Why? Because I don't like fractions. Well, I love fractions, but I don't want this fraction. And doing this gets rid of it. Maybe this will work for us, maybe it won't, but let's see where it takes us. So this will be then the limit as x approaches 1. If I multiply this through 1 over x times x, it's just 1, and then subtract x. Okay. On the denominator, we're going to get x minus 1 times x. Now you can see where this is leading. All I have to do is pull out a negative 1 there. So the limit as x approaches 1 of negative x minus 1 all over x minus 1 times x. Great. Now these cancel, and I'm just left with minus 1 over x. If I substitute x as 1, you get minus 1. Alright, so this question says sketch the following function. Now I've sketched it for you. Well, I haven't. Desmos has sketched it for you. Right? Simply because I am terrible at drawing on my computer. If you forget how to sketch these, don't worry, we'll be doing a whole section later in calculus on curve sketching, and on your test for chapter 1, I would probably just give you what it looks like. But if I don't use Desmos. So this one says, the limit as x approaches negative 1 of f at x. Okay, well negative 1 is here. Now, looking at that, as we approach it from the left, we get a different value from what we approach from the right. So this limit here does not exist. What about this one, as we approach 2? Well, as we approach 2, it looks like they're the same. And it certainly is, because one of them is less than or equal to 2. Even if it wasn't equal, that just means the function doesn't exist there, but the limit still does, because they approach the same value. So this one does exist, and it equals 8. If it doesn't appear perfectly nicely on the graph, you can always just look at it and say, oh, 8. Or if I don't have something nice like that, you can substitute 2 in here, right? 2 cubed is 8. Then it says, is the function continuous at these points? Okay, well this one's definitely not continuous because the limit doesn't exist. Remember, for something to be continuous, the limit must exist and your function must exist at that point. And they must be the same thing. So this one, no, not continuous. This one, however, yes. This is continuous because the function at that point exists, it's defined and it's equal to 8, and the limit exists and is also equal to 8. So yes, in that case, it is continuous there.